Hi, I'm Dr. Harold, and this is a follow-up of the first video on just general basics of reflection and refraction. Remember, reflection is usually talked about concerning a mirrored surface where the angle of incidence in is exactly equal to the angle of incidence out. The angle of incidence is drawn with the perpendicular normal to whatever surface is being struck. Now, going here, we have a new law called Snell's law, which basically is the ratio of the incident velocity of light coming in from the first medium, that can be a vacuum or other things, or air, and then strikes a second medium and changes its velocity. Remember, when the density of the structure changes, such as from air to glass, it's more dense, and that bends the light. It changes the velocity. And when you change the velocity, you bend the light. Okay, so we have the ratio of the incident velocity versus the velocity of the second medium. Okay, we have different media as shown in this. Here we have things such as vacuum, air, water, plexiglass, glass, or diamond. Okay, in England they often call this plexiglass. Okay, now what we do is Snell's law talks about that refractive index, which is indicated by the letter small case n. Okay, the refractive index. That refractive index literally is the speed of light in a vacuum, which we know is 2.995 times 10 to the 8 meters per second. For classical physics, it's so close to our 3.0 times 10 to the 8 meters per second, that will work. Okay? So, what that means though, is actually in air, it's a different speed than out in outer space where there's a vacuum. Okay? And the refractive index of this ratio in air, for instance, is more than the amount of in a vacuum. So, in a vacuum, we consider it's 1 because we have its speed in the medium and it relating to the original speed. So it's over itself, so it's 1. In air, on the other hand, okay, we have a different velocity, so we have a different refractive index. Water is quite dense. This is geared in levels of density. Notice diamond is the hardest surface known to mankind, and one of the things, it's quite dense, but it's still translucent. Women love their diamonds because it sparkles that light and reflects off the different angles inside, and the facets that they place on the outside of the diamond change the angles of the incident light in a diamond, but it's very hard. And notice the number is quite large compared to air, for instance. Okay, so we can take the speed of light in a vacuum at 3 times 10 to the 8 meters per second, divided by the speed of light in that medium, and then we get the n values, the refracted index values for these different medium. Okay, there's more than this. This is just some of it. Obviously, we use optic fibers, etc., in telecommunications, and we bounce beams of light off of the inside surface of the optic fiber, for instance, and digitize it in binomial language. But going back to this, so if I have 2 medium, which usually that's what we're talking about, for instance, in my glass case here, we have air versus glass. The incident angle coming in from the normal, okay, not from this surface. The normal is perpendicular to the surface that it enters at that point. So the incident angle is theta, okay, which is denoted as here in Snell's law expanded equation, sine of theta 1. Now, when we find out the angle that is refracted, the bent angle from the normal once again, that is theta 2. So if we know what the first medium's refracted index is, such as air, we can find the refractive index of whatever that translucent surface is, such as glass. Okay, we can also calculate what the speed is if we know the speed of one versus the speed of the other. So this is a handy dandy equation, and notice something: the refractive index of the first medium versus the second is 1 over 2, whereas theta is 2 over 1, and velocity is the second one versus the velocity of the first. Okay, so that's the basics of Snell's law. Later we will be working some equations and solving some problems, and hopefully in your school or in my lab we'll be doing a lab on investigation of light that is being bent, refracted.